We'll start our first talk this afternoon, just by Fernando Shao, who'll speak on highest Fourier uniformity of primes and almost all arithmetic progression.
Thank you, Sam, for the introduction. Thanks to the organizers for, I think the title is correct. But let me just first begin by thanking the organizers for inviting me to speak. But yes, as some of you may have noticed, my talk has some similarities with Terry's talk early in the morning. In fact, my talk just happens in the alternate universe where instead of short intervals, you have arithmetic progressions instead. So everything I talk about today are based on two projects, one with Joni Teravainen, the other with both Pierre, Bienvenu and Joni. Type of question I'm interested in is about the distribution of arithmetic functions in arithmetic progressions. So if f is an arithmetic function of interest, for example, the von Mangold function or the Mobius function or other multiplicative functions, and A mod Q be a co-prime residue class, we would like to estimate the partial sum over the residue class A mod Q of the function f of n. And in most cases, we expect that this is asymptotically equal to 1 over phi of q times the sum over all co-prime integers n with q. And if this estimate 1 holds, then this function f is equidistributed modulo q. Okay, so sorry, I forgot. I'm supposed to say something about Andrew first. So yesterday I ran into Andrew in the hallway, and he made the claim that I am his most frequent collaborator in the past decade. Now, I have no idea if that's true or not, because as is always, he makes bold claims. Many of them are false, but it did start to make me thinking. So our collaboration started on December the 30th, 2016. So the eve of New Year's Eve, 2016. I got an email from Andrew asking me a bunch of very interesting questions with regard to some of my previous works and some of his and his students' previous works. I was just a little postdoc back then, so I thought I needed to respond to that email in a timely manner. So I spent that day figuring out what the situation was and was able to form some response. And at that time, Andrew was in the UK and I was in the US, so there was a time zone difference. So I happily went back to sleep, knowing that Andrew will not be able to see the email until he gets up. But the next day, December the 31st, 2016, when I get up, I saw 5 emails from Andrew elaborating on the discussions we had the previous day. And okay, so the story continues in exactly the same way. I still think that I needed to reply to that email in a timely manner. So I spent December the 31st on those questions. And the exact same thing happens on New Year's Day, on the day after New Year's Day, on the day after New Year's Day, and so on. Continued for maybe 2 or 3 weeks. So thank you, Andrew, for making my life very interesting on those days. And when I was going through those emails yesterday, I noticed that one of those days, I think it was January the 7th or something, my email was like, yes, I believe we can do this, that. I will try to write something down as soon as possible. Knowing past me very well, I think this was me saying that, give me some time, I'll write that down. But I thought I bought myself at least a few days. But 24 hours later, the reply from Andrew comes in and he says, how are you doing with the write-ups? Okay. But on a more serious note, thanks to Andrew for sharing his passions in addition to experience in analytic number theory. So returning to the subject of distribution in arithmetic progressions. So in this talk, I will be mostly interested in this arithmetic function f being either the von Mangold function or the Mobius function. In fact, as is the case with Terry's talk earlier, many of the results I state here hold for both of them. I will try to state most of them for the von Mangold function, but corresponding results hold for Mobius as well. So the famous Siegel-Wolfe theorem says that the primes are equidistributed in arithmetic progressions for q up to any fixed power of log n. This is due to the presence of Siegel 0 and is in general very hard barrier. Assuming GRH, we can get the estimate number 1 for q all the way up to n to the 1/2 minus epsilon. And this 1/2 in the exponent is usually referred to as the level of distribution. But unconditionally, we have the famous Bombieri-Vinogradov theorem, which will be the subject of later parts of the talk, that says that if you average over all moduli q up to n to the 1/2 minus epsilon, then estimate number 1 holds in that sense. Okay, so, well, again, as in the case with Terry's talk in the morning, we can ask more refined distributional questions about von Mangold in arithmetic progressions. So on this slide, I show 2 results in this direction where you have a twist by an exponential phase. So estimates for sums like this, twisted by an exponential phase, is useful in certain applications. For example, in applications involving the circle method. So Todorova and Tolev proved that if you twist von Mangold by an exponential phase, E of alpha n, with alpha being fixed, then you have this kind of equidistribution with level of distribution 1/3. So here capital Q is n to the 1/3 minus epsilon. So 1/3 is not as good as 1/2 from the previous slide. And also I'm a little bit lazy here in terms of what the main term is. So in fact, what they actually show is that if alpha is in the minor arc, then this holds with the main term equal to 0. There is a related result by Matomaki in 2009. She showed that you can improve the level of distribution to 1/2 if instead of the absolute value sign, you have a well-factorable weight lambda q, and instead of the maximum over a, you have a fixed residual class a modulo q, for example, 1 modulo q. So this well-factorable weights thing is something that shows up in sieve theory. So results of this kind can be still useful even without the absolute value sign. So for example, Matomaki was able to use this result to prove some Diophantine approximation problem with rationals with denominators being an almost prime. Okay, so what I am going to be mainly interested in this talk is to generalize this kind of result with the Fourier phase, E of alpha n, replaced by nilsequences. Okay, so the question I want to discuss here is that there are 2 questions, 2 types of questions. One is to, as I said, extend the results above with E of alpha n by polynomial phase functions, E of g of n, where g of n is a polynomial, and more generally by nilsequences psi of n. So why do we care about nilsequences? Because Terry told us so in the morning. I actually missed the first few minutes of your talk, so I don't actually know what you said, but right. So nilsequences are objects that arise from the inverse theorem for Furukawa's norms, which is an important theory in additive combinatorics. So understanding sums involving nilsequences allows us to understand certain additive or linear patterns in. I will not formally define what nilsequences are, but these polynomial phase functions are special examples of nilsequences, but there are other nilsequences as well. But in addition to this, I also want to talk about results when the phase alpha to the 2 results on the previous slide is allowed to depend on Q. So you may recall that in these two results, the alpha is fixed from the beginning. After I describe our results, I will talk about some applications. The first two applications here are relatively more straightforward. And I'll spend more time talking about the third application, which is joint work with Pierre and Joni about linear patterns in almost twin primes. Okay, so my next slide is a statement of our results, generalizing the results on the previous slide, but this is the previous slide. I can just quickly tell you what our result is. Based on this, we are able to extend these two results with E of alpha n replaced by a nil sequence. And additionally, we're able to obtain a third result, which gives a level of distribution 1/4. In the case if you allow the nil sequence to depend on the modulus Q. Okay, so this is actually the result I just said. If capital Q is entered to 1/4 minus epsilon, then we have this estimate. So I stated in theorem 1 this estimate for just polynomial phase functions, but we actually get the result for more general polynomial, more general nil sequences. So the result is that if you look at the sum over, if you sum of lambda twisted by E of G of n in arithmetic progressions A mod Q, then this is well distributed. And the residual class A mod Q and the polynomial G are allowed to depend on the modulus Q. Okay, so the lower half of the slide is just the actual general result we prove. But since I'm not defining nil sequences, I'll just skip that. So this is a nice result. I think this is new for, I think this is a new result. Okay, so what I'm trying to say that for some of the applications we have, any positive level of distribution would be enough. And this result would would be sufficient for that purpose. But of course, this 1/4 in the exponent of Q here is less than the 1/3 that we saw on the previous slide. So there's definitely a question that can be asked in terms of improving it. And next, this theorems 2 and 3 are the direct generalization of the Todorova-Tolev result and the Matomagi result when E of alpha n are replaced by polynomial phase functions, and more generally for nil sequences with level of distribution 1/3 and 1/2 respectively. And these three results are joint work with Joni. So I just want to mention a few connections with other things. So some of them already appeared in the morning in Terry's talk. In a special case when Q is equal to 1. So in that case, we don't actually have the arithmetic progression. We're just summing over all integers up to some capital N. So in this case, we know about estimates for the Mobius function or for the von Mangold function twisted by nil sequences due to results of Green and Tau. And more generally, there is a result of friend Tsikinakis and Host. They showed that any multiplicative function f, any one-bounded multiplicative function f discorrelates with a fixed nil sequence unless there is an obvious reason not to. So the obvious reason not to is when the multiplicative function f is periodic. So they proved this discorrelation for any aperiodic multiplicative function, and here a function is called aperiodic if the partial sum over any fixed residue class A mod Q of the function f is little o of the trivial bound. And these results are interesting because via the inverse theorem for Galois norms in additive combinatorics, they imply that the Mobius function mu or any multiplicative function f in the result of Tsikinakis and Host are Galois uniform. And from that, we can deduce many nice additive combinatorial applications. So in this direction, we can view the theorems 1, 2, and 3 from the previous slides as generalizations of these results when Q is. Okay, so just to put some of the results I mentioned in the ugly table. So the first column, d equals to 0, corresponds to the degree of the polynomial g of n equals to 0. In other words, that's just a constant. So the first column is the classical Bombieri-Vinogradov theorem. So I should say that in this direction, there is a lot of work in terms of going beyond the 1/2 threshold, so going beyond the Bombieri-Vinogradov theorem. In the case when the residual class A is fixed and with well-factorable weight instead of the absolute value sign, there is a famous result by Bombieri, Friedlander, and Iwaniak, who can go to the level of distribution 4/7. And this kind of thing was also a component in Yitan Zhang's work on bounded gaps between primes. And more recently, James Maynard also has some results in this direction. And there may be other people that have results in this direction as well. Sorry if I forgot to mention you. The second and the third column are the situations considered in this talk. So the d equals to 1 case, the Fourier phase case, was the earlier results. And the case of general polynomial phase was our theorems 1, 2, and 3. So there is definitely a question that can be asked here in terms of improving these thresholds, 1/3 or 1/4 or 1/2 in columns 2 and 3. But just to mention a related result, a few years ago, or 5 years ago, I proved that if you consider the Mobius function instead of the von Mangold function, and if you only care about saving of log n instead of the saving of arbitrary power of log, then you can get the level of distribution 1/2, even if you allow the residual class A and the polynomial G to depend on. Okay, so I want to move on to talk about applications, and then after that, I'll talk about some ideas in the proof. So these are the two applications I want to skip over. Just mention quickly, corollary 1 is a direct application of the theory of Galois norms. Corollary 2 is that we can do something about finding almost twin primes in Bohr sets. Okay, so I skipped them due to time constraints. The third application I want to mention relates with the Green-Tao theorem about linear forms in primes. So if I have L1 of x up to LT of x, let them be T of affine linear forms in D variables, and suppose that no two of them have linearly dependent linear parts, then we can count asymptotically the number of primes represented by these linear forms in a box. For example, if these linear forms are x1, x1 plus x2, up to x1 plus k minus 1, x2, then this counts the number of KAPs in primes with x1, x2 up to a threshold. So using these Bombieri-Vinogradov type theorems, we're able to obtain the following generalization, or well, short generalization. So let P be the set of Chen primes. So this is the set of primes P such that P plus 2 has at most 2 prime factors. So by the famous result of Chen and work of people following him, we know that there are infinite many Chen primes, and we have a lower bound of the correct order of magnitude for the number of them. Now, our result is that we can, if we want to look at the problem of counting the number of Chen primes represented by these linear forms L1 through LT, then we have the correct order of magnitude for a lower bound. So we have a low, so thank you. The denominator should be log x to the 2t because, yeah, right. So in fact, many special cases of it were known before. For example, Zhou in 2009 showed that there are infinite many k-term arithmetic progressions in Chen primes. So this is a special case when the L1 through LT are representing the k-term progressions. But our result is new when the linear patterns involved is not translation invariant. An example of which is this: x1, x1 plus 2, x1 plus 2x2, and x2 minus 1. So if you just change the fourth linear form from x2 on the slide to x2 minus 1, then actually x2 minus 2, okay, you change it to something so that there is actually no local obstructions for the existence of Chen primes. So let me start with the proof ingredients of this application, and then I'll talk about the proof ingredients of the Bombieri-Vinogradov type result. So basically, there are 2 ingredients in this proof. I forgot to mention that application is joint work with Pierre and Joni. So one of them is combinatorics. We use an idea from works of Green and Tao and others to develop a variant of the transference principle, which allows us to reduces the original problem to the problem about finding Chen primes in level sets of nilsequences. So more precisely, let this f of g of n gamma be a nilsequence taking values in between 0 and 1. Then we want to show a lower bound of the number of Chen primes. So recall that P represents the set of Chen primes. We want to get a lower bound for the number of Chen primes weighted by this nilsequence with the correct order of magnitude lower bound. So this looks like a sieve problem. And so indeed, that's how we solve this sieve problem. Well, indeed, this is a sieve problem that we solve using similar ideas from the work of Chen and Ivaniak's simplification later on. But in using these sieves, we needed some estimates controlling the error term, and those error terms are exactly controlled by the Bombieri-Vinogradov estimate I showed you earlier. Okay, so in terms of proving the Bombieri-Vinogradov type estimate, so let me pick one of theorems 1, 2, and 3. So okay, so I forgot which one this is, but this is the one with level of distribution 1/3. So this is the one where the residual class A is allowed to depend on Q, but the polynomial g of n is fixed. In that case, the quantity we're interested in estimating is this one. The 3 steps that are involved is, first of all, we reduce to the case when the polynomial g is equidistributed. In other words, when it's in minor arcs. In major arcs, this basically reduces to the classical Bombieri-Vinogradov. So this is rather easy to do in the case when the polynomial g, when you're actually considering this problem with polynomial phases, because a polynomial is either in major arcs or in minor arcs. But it's more technical for nilsequences. One has to use some tools developed by Green-Tao and Green-Tao-Ziegler on nilsequences. And the step 2 for dealing with equidistributed G is to use standard Voron's identity to reduce type 1 and type 2 sums, and then we estimate the type 1 and type 2 sums using the only tools we have, Cauchy-Schwarz and Weyl inequality, and the nilsequence version of Weyl inequality, also due to Green and Tao. So just to give you a glimpse of how things go in terms of type 2 sums, if you ignore the main term, well, in fact, in the case when G is equidistributed, the main term is expected to be 0. So there is no main term. The type 2 sum will look like this. Basically, replace the Von-Mangold function lambda by the convolution of the 2 sequences A and B. So, these 2 sequences are supported on dyadic ranges around capital M and capital N. Capital M and capital N are between x to the 1/3 and x to the 2/3. Now you throw away one of the coefficients using triangle inequality. In this simplification, using triangles inequality, but actually the sequences AM and BN are not one bounded, so you use Cauchy-Schwarz. But anyways, okay. So you arrive at the inequality in the middle, and then you apply Cauchy-Schwarz, move the order of summation. Change the order of summation, rearrange to get rid of the coefficients Bn. You arrive at this inequality at the bottom. This is a sum over all the moduli Q, a sum over all n and n prime, and congruent to n prime modulo Q, and the sum over m satisfying m times n congruent to aq modulo Q, and then this exponential phase as the summand. So here I can already give you an indication why the threshold for this problem we get is 1/3. For this sum, for us to be able to estimate this sum, we need this inner sum over n prime and the inner sum over m to have length at least 1. And the length over n prime is n over q, so we better have q less than n. The length over m is m over q, So we better have Q less than M. So that means we need Q less than the minimum of M and N for this sum to be possibly estimable, if that's a word. And because M and N in the worst case can be x to the 1/3 and x to the 2/3, we can deal with this estimate if Q is less than x to the 1/3. So this is the last slide, continuing from the previous argument, just to show you that indeed, as long as that condition is satisfied, we can complete the argument. But the argument presented here are rather elementary, only use Weyl inequality, and only uses Weyl inequality. But as I said, to treat general nil sequences, we need something stronger. Fortunately, all of this can be extended to nil sequences using tools already developed. But as I mentioned earlier, it would be very nice to improve on the level of distribution for any of these problems. So I think this is all my slides. Thank you for listening, and happy birthday, Andrew. But if you want to prove the level between 1 minus epsilon 1 for these problems, you have to prove the Elliott-Halberstam conjecture first. Yes. Yes, good point. Thank you. Sorry, can you repeat? Is there an easier? Yes, so basically these three results, the theorems 1, 2, and 3, the only difference in the proof of them are how Cauchy-Schwarz are arranged in this in these steps. So for the 1/4 result, the polynomial G will depend on Q as well. So you cannot exactly do Cauchy-Schwarz like this. But there is if you try this, there will be a natural way to do this. And the easy explanation for 1/4 is that 1/4 is 1/2 over 2. So basically, you will have a sum whose length is m over q squared, and one of m and n has to be x to the 1/4. Thank you.